but
Okay. Well, for the atomic spectroscopy of hydrogen, and you're going to find that in chemistry, they use spectro a lot of different ways. Spectrophotometry, spectroscopy, spectrometry. I'm not sure why they have different ways of naming them, but they're all essentially the same type of thing. We're looking at light. So here, you want to take a look at the lectures to find out what's going to be turned in, and also the assignment for what's going to be turned in. There's 2 lectures in that video lecture part. So you want to watch the demo part, and then you want to watch the part where I go over the concepts. And again, for the introduction, I wouldn't write all of this stuff in your introduction. I'd write down the important things that you're using for this lab. Like for instance, there's an equation in here for calculating the radius, and you're calculating the radius. I'd definitely include that. I'd also include the equation that I give you for calculating the radius, because it's a lot easier than this equation. And the same for the energy. I give you an equation for calculating the energy, which is pretty much the same as this one. But I ask you, when you write down the answers for the energy, is that you put it in decimal form times 10 to the minus 18. So, and then this last one, change in energy. I don't like their formula whatsoever because they're playing with it, and I don't like that. And so I show you my derivation of the formula and how to use it. And that change in wavelength is what's calculated down here where it says wave energy. Now these wave energies are kind of funny because they're all positive in this sample, but they should all be negative. And we're going to calculate negative wave energies, and that's fine because they're supposed to be negative. Okay. So I hope that helps a little bit, Harry. What's next? Jackie, do you have anything?
No, I don't have any questions.
Got any answers?
Not really.
No, okay. All right. Let's see. So, Harry, do you have any other questions?
Nope, I just said that one about the lab.
Okay, well then what I'm going to do is I'm going to give you a little bit more about chapter 7. Oh, chapter 6, or module 7, I should say. I just posted, I think earlier today, a link to the first Q&A where we talked about radiation, Planck, atomic line spectra, and Niels Bohr. So we kind of left off with atomic line spectra and Niels Bohr. And, in the Q&A, I showed you a video, not a video, a cartoon of absorption, emission spectra, and a continuous spectra. And I showed you how to do a few of the calculations. Let's go to section 6.4, which is the particle wave duality. So these are like little mini lectures I'm giving you. And I'm giving you the more important things out of the lecture. So not a whole lot of detail, more of the, here's what you want to work with, or what you want to start with. So with the particle wave duality, the idea was that we could treat particles like waves. And let's see, there used to be an image in the previous editions about how we could treat particles like waves. And let me see if they have that here. Okay, so I'm going to have to look this up on the internet real quick. So I'm going to look up diffraction. Let's see, electron beam diffraction versus light diffraction foil. And let me see if I can get some side-by-side images here. Here's the one that I usually like to show people. So I'm going to change my share here. And of course, this is from the University of Washington, which is a pretty good school. Okay, so let me change my share. Okay, so take a look at these diffraction patterns, okay? So if we take a look at here and we read this, diffraction patterns simulated above, compare the effects of X-ray passing through a thin foil with high energy electrons passing through the foil. So these are simulations, mind you. But on the left, we have X-rays passing through tin foil and we see a diffraction pattern. And on the right, we see light passing through the foil and we see a diffraction pattern. So if light produces this diffraction pattern and electrons, which are particles, produce this diffraction pattern, the idea is pretty simple that, maybe we can treat particles as if they are waves instead of as if they're particles. So here is a real image. Oh, shoot. Let me see if I can open this up. So I want to show you, rather than simulation, the real deal. Because, seeing with your own eyes is far more believable than just looking at something that's a simulation. Okay, where's my documents or desktop? Chem 1A, lectures, module 7. I think that's where it ended up being. Okay, so this is a PDF that I'm opening up. All right, and there's a whole lot of physics in here, but this is what I want to look at right here. Can you see what I'm looking at? Can you see two bullseyes, as it were?
Yeah, but also the other images.
So the one bullseye should say diffraction pattern of X-ray beam passing through aluminum foil.
Yep.
The other one should say diffraction pattern of electron beam passing through aluminum foil.
Yep. Let me see them.
Okay, so here, these are the real things. These are not simulations. And you can see they look remarkably alike. And so here, the idea is if these look remarkably alike, then maybe if we're going to treat X-rays as if they are X-rays like they are waves, then maybe we can treat aluminum foil like they are waves. And the idea here behind the wave idea behind this is that if you think about dropping a pebble into the water, what happens from where you drop the pebble in the water? You get a radiation of waves, right? And so here, that's kind of what both of these look like. You drop a pebble in the water and you get a wave pattern. So that's why they call, that's one of the reasons why we say that, hey, maybe particles can behave like waves. Okay, so I'm going to close that. I'm going to go back to the other share, which is the Elmo here. Okay, so back to the particle wave duality. We're going to treat particles like waves, and we've got something called the de Broglie wave equation. And it is this: pi is equal to h over mv. Now we got to be careful about what we're doing here, because this v looks like a volume v, but it's not. So h is Planck's constant. M is the mass, and v is the velocity. Now, when you use this equation, wavelength is the wavelength, lambda, I should say, is the wavelength. And this is going to be in meters per second as long as Planck's constant is in joules seconds, which it is, as long as the mass is in kilograms. So that means you need to turn the mass into kilograms. If it's given as grams, you need to switch it. And the velocity has to be meters per second. As long as that works out, your wavelength will be in meters per second. And it's because a joule is actually a kilogram meters squared per second squared. That's what a joule really is. So this is the big deal out of that particular section, is being able to use this equation. So let's say that, for instance, you wanted to calculate the wavelength of Usain Bolt. So he's an Olympic sprinter. He's really fast. I believe he has run the 100-meter dash in about 9.8 seconds. Okay, so what is his wavelength when he's running this, if this describes his average speed? Well, we need to know his mass. What is the mass of Usain Bolt? And we want it in kilograms. So he's about 80 kilograms. He's a rather large guy. He's tall. And although he looks skinny, he's very muscular. And we'll just put 80 kilograms. His velocity is 100 meters over 9.8 seconds. Now, this 100 is definitely 100 point. They do measure it that carefully. And he may be a little faster than this. I'm not sure. But you know, for me to run 100 meters, it wouldn't be 9.8 seconds. It'd be more like 29.8 seconds. And then here, Planck's constant is 6.626 times 10 to the minus 34 joule seconds. So what I'm going to do is have you guys, for the moment, calculate the wavelength of Usain Bolt. So go ahead and calculate that wavelength. Whoops, that should be V. And when you're done, give me a thumbs up, all right? Are you already done with that, Jackie? Okay, I'll be right back. Okay, give me the thumbs up when you're done. All right, are you guys still there? You're still there, Jackie? Did you calculate it? Okay, so let me tell you what I get. So I get 8.1 times 10 to the minus 37 meters. Is that what you guys got? Good. Okay. So what part of the electromagnetic spectrum? So let's take a look at the electromagnetic spectrum and see if we can figure out which part this comes from. So where is that spectrum? On page 278. So 10 to the minus 37 meters puts this definitely in gamma rays. Okay. So he's emitting gamma rays. Now, are we really afraid of watching an Olympic sprinter because of the gamma rays? And the answer is absolutely not. Okay. So that's that section, the particle wave duality. To summarize it, let me show you how the units work out, just so that you can see that. So here we actually have 8.1 times 10 to the minus 37 joules seconds over kilograms meters per second. And that's equal to 8.1 times 10 to the minus 37 kilograms meters squared per second squared times second over kilograms meters per second. So when we look at what cancels, this second cancels with one of these, so we have one left over. This second in the denominator cancels with this one in the denominator. One of these meters cancels with that meter because they're both in the numerator. And here, this kilogram cancels with this kilogram. So you can see the thing that we're left with is a meter. And so you'll notice if we have our mass in kilograms and we have our velocity in meters per second, everything's going to be good. And that's the important thing in addition to this equation that you must remember is you must have the correct units so that you end up with meters. Okay, so that's important to know. All right, the next section is the quantum mechanics. Okay, so quantum mechanics is born out of the necessity to improve the model for Bohr's atom. So for Bohr's atom, the electrons orbit the nucleus. Only specific orbits are allowed. This is quantization. So the way I like to describe that only specific orbits are allowed is it's like steps compared to a ramp. So when you're walking up steps, you can only stop on a step. You can't stop in between a step. And I'm also considering that you're going to have both feet on the same step, okay? Not one of those while they're stepping that the height of the person changes. So at rest, you have both feet on one step. You can either be at the bottom, first step, second step, or fourth step in my picture. But at rest on a ramp, you can be any height above the ground. Any height. And we all know that when you have a line, even that a line that has a beginning and an end, there's an infinite number of points on that line. So your distance above the ground has an infinite number of choices when you have a ramp. Bohr's atom says you can't have that. You can't have an electron orbiting just anywhere. It has to be at a specific radius. And when you have these specific radii, you also have specific energies for the electron. And that energy is calculated by doing this negative RHC over n squared, which is minus 2.1788 times 10 to the minus 18 joules over n squared. R is a constant, Rydberg's constant, H is a constant, Planck's constant, C is a constant speed of light. So you multiply these things together and you get that. And then Bohr also said that atoms can emit energy or absorb energy if you have a change in E. So if you have a change in E, that's E final minus E initial, and that ends up being minus RHC 1 over n final squared minus 1 over n initial squared, or negative 2.1788 times 10 to the minus 18 joules times 1 over n final squared minus 1 over n initial squared. And you want to keep track of the sign when you're doing these calculations, because if you have a negative sign, that means energy is emitted as a photon. And if this is a positive, it means energy is absorbed from a photon of that energy. So that's Bohr's atom. But there are some problems with Bohr's atom. And one of the problems, of course, is that you have this proton and you have an electron that's orbiting the atom. So over time, this is what's supposed to happen when you have things that are oppositely charged like this. The electron should spiral in to the nucleus, and you end up with basically a neutron, because a proton and an electron pretty much equal a neutron. So that's what should happen over time, but that doesn't happen. So here's one of the problems with this model. Another problem with this model is if you have a proton here, and remember, this is more than just a hydrogen atom. This would be other atoms too, but let's say it is just a hydrogen atom. You have this electron orbiting the atom. So when you take a look at this guy right here, it looks like a disk, not a sphere. So that means our hydrogen atom should look like a plate, not a sphere. But the sphere model works best when we look at atoms, not the disk model. So that's another problem with Bohr's atom. Plus, you got this idea that you can have the electron in these different orbits, 1, 2, 3, 4, but there's no good reason given why. Why? No good reason. So here are some problems with Bohr's model. And some other cats came along, and this is sometimes called Schrodinger's model of the atom, or Schrodinger's quantum mechanical view. Of your hydrogen atom. And a really good question is, well, why do we keep seeing a model of the hydrogen atom? And the answer is because it's the simplest atom. One proton, one electron. You don't need to worry about what one electron does to another electron, or what one proton does to another proton. So Schrodinger's quantum mechanical view of the hydrogen atom is you treat the electrons as standing waves. So a standing wave is one where it looks like it's not moving really. So here, this is the simplest standing wave you can have. So here's one wall, here's say the wall, and here's a person. And let's get rid of that. This is a standing wave. It's like a jump rope. When you look at it from the side and the jump rope's going fast enough, it looks like it's either up or it's down. It's going back and forth and oscillating back and forth. This is like a guitar string or like a musical note hanging in the air. So you could also have a standing wave. The next standing wave that we could have here would look like this. But that's a standing wave. So these points are fixed. But this is another standing wave. And here's yet another standing wave. Now notice every standing wave that I draw, these points are on the same line, right? So that means that you can't have this. So here, this is not a standing wave. These are standing waves. So if I draw something like this, where these two distances are the same, and I go like this, boom, boom, this is not a standing wave. So we would say that whatever this wavelength is, so this wavelength is okay, this wavelength is okay, this wavelength is not okay. So this wavelength is not a solution, as it were, not a solution to our problem. So he wanted to treat electrons on an atom as standing waves. And I'm going to change my share screen back to Firefox. And let's take a look at the standing wave of an electron on a hydrogen atom. And I think Khan Academy actually does a decent job of showing this. Let me see if I can type in Khan. Here we go, the quantum mechanical model of the atom. So you do have a lab that I'm going to have you do tomorrow that includes reading this article. Let me see. So there's a standing wave. You see how it's oscillating back and forth? You guys see that? Just give me a little thumbs up if you do. Okay, so that's a standing wave. And with Schrodinger's equation, here's the idea that the electron is basically a standing wave around the nucleus of an atom. Now, here, this wavelength works. And here's an example of one where the standing wave doesn't work. The wavelength is not the correct length, and it ends up being destructive. So it's not a solution for the problem. Okay? All right. So for his particular model, he used something called a wave function. So this is the quantum mechanical view. First of all, I should say for this model, it's three-dimensional. It's not a disk. He used something called a wave function. And with this wave function, the symbol he used for the wave function was the thing that looks like a pitchfork, which is the symbol psi. And this wave function, since it's three-dimensional, it has three variables, just like your Cartesian coordinates, x, y, and z are needed for 3 dimensions. Here, he uses x, y, and z, but he didn't name them x, y, and z. He named them instead n, l, and m sub l. And n is the principal quantum number. L is the angular momentum quantum number. And M sub L is the magnetic quantum number. So those are the three variables in this particular equation. And in the book, they call this the orbital angular momentum quantum number. That's kind of new on me. I'm used to just calling it the angular quantum number. So the wave function has these three things. And yeah.
Have you been writing this all down? Because we're still on the Khan Academy page.
Oh, sorry. I have been writing it all down. Let me share it with you. And you might want to write this stuff down. And while you're writing it down, I will pause the. All right. So here's some important aspects you need to know about the quantum model. First of all, psi. When you calculate psi, this gives the energy of the electron in its well, I'll just say it just gives you the energy of the electron. And only specific energies allowed. Because we have standing waves. Do you remember that equation E equals hc over lambda? And with these drawings here, only specific wavelengths are allowed, right? And here's an example of a wavelength that is not allowed. This wavelength is not allowed because for our standing waves, all of these points have to line up, the end points, just like a jump rope. And here's an example where there's no point on this wall where it lines up with that point. So this is not allowed. If you have only specific wavelengths allowed, what does that mean about the energy? Well, if you only have specific wavelengths allowed, then you only have specific energies allowed. Okay? So do you remember how with Bohr's atom, only specific orbits were allowed? And because of that, only specific energies are allowed? Well, here, you don't have that artificial hamstring where you say, well, only specific energies are allowed. You say, well, if we treat them as standing waves, then only specific energies are allowed. So this gives the energy of the electron. And then there's also this thing called psi squared, where you take the wave function, square it, and this gives the probably the best way to say this is radial distribution. Distribution of the electron. So the probability of finding the electron near the nucleus.
What does the capital E stand for again?
Well, stands for energy.
Oh, okay. That's what I think. Thank you.
So these are the two important things when we talk about psi. Psi gives the energy of the electron, and psi squared gives the radial distribution or probability. And the radial distribution gives rise to a, actually your book names these a little differently. So this is a radial distribution, gives rise to a surface density. Okay, so those are the two important things here. And when I talk about radial distribution in a surface density plot, I'll show you what I mean using Khan Academy. So I'm going to do a new share. And remind me to go back. So Khan Academy has brought together some of these visuals that are really nice that I've used in classes, and you find these in different textbooks. But do you see this graph here where you see a purple, green, and red lines? Are we okay there? Okay. So this is a radial distribution plot. And I want to try and help you to understand this. So can you see my cursor that looks like a magnifying glass with the plus sign? Can you see that? Good. So right where it is now, that is right at the nucleus. And you can see that for all three of these lines, the probability of finding an electron is 0 when you're at the nucleus. And that makes sense. You can't find an electron in the nucleus. Now, if we focus just on the purple line, do you see how it's a nice big peak and then it flattens out at 0? So that is a radial distribution, the likelihood of where you are to find the electron. So where the peak is high, you're likely to find the electron. Where the peak is low, you're not likely to find the electron. So that's one energy level for the electron. And so here, n would equal 1. So n is one of those quantum numbers. Now, for an n equal 2 energy, you're more likely to find the electron farther away from the nucleus, as you can see by the green graph. You can certainly find the electron close to the nucleus like the 1s, but it's a low probability. You're far more likely to find it a little farther from the nucleus. And then if the energy level is 3, n equal 3, you got a 3s radial distribution plot there. And you see how with the 3s, you have two smaller probabilities of finding the electron close to the nucleus and a larger one farther from the nucleus. So do you see these radial distribution plots? Now I want you to imagine you want to take these radial distribution plots and make them three-dimensional. So what would that 1s radial distribution plot look like in 3 dimensions? So you've got to take this radial distribution plot and kind of imagine the electron being this far from the nucleus at any direction from the nucleus, any x, y, and z. So what would this plot look like? And here, this is a very common thing that we see in textbooks. Do you see this 1s? That's it. So you might ask yourself, this region here where it peaks out, and this region where it gets really small, why don't we see a really thick bunch of electrons at this far from the nucleus, and then it goes away when it gets closer to the nucleus? Why don't we see this in this picture here? And the answer is this picture isn't really a cross section. It's really the whole three-dimensional plot. So here, once you draw that middle is going to look like it's crowded, but you're not going to find the nucleus right in the middle. This 1s is not a cross section. Now look at the 2s. Do you see how you're going to find the electron kind of close to the nucleus and then farther away from the nucleus? Here's the 2s above. Now this isn't in 3 dimensions, this is in 2 dimensions. So can you see that with the golden color, it's supposed to be a little less dense, and the blue color, it's supposed to be far more dense. So here, for an energy level of n equal 2, you're far more likely to find the electron farther from the nucleus. Is there some overlap of regions between 1s and 2s? And the answer is absolutely. So if you look at the 3s, you can see that we have a low probability, a better probability, and then a great big probability. And we can see that here with the densities. They did a pretty good job here where the middle is very less dense than the middle, and the middle looks a little less dense than the outer ring. So not only are these giving the energies of each electron, but it's giving you an ideal, if you will, or a most likely distance that the electron is located compared to the nucleus. And it's important here to understand that when you have an n equal 3 electron, for an atom that say has 2 electrons, if you have one in the first energy level and one in the third energy level, they can still share the same space, but they have different energies. And you might wonder, well, how in the world can that be? And the idea here is when we talk about the Heisenberg uncertainties principle, basically what's built into this model is that if you know the energy of the electron precisely, you don't know where it is. But if you know where it is, you don't know its energy. So you can't simultaneously know the location of the electron and its energy with certainty. So this model focuses on, let's know the energy with some certainty, and instead of knowing where the electron is, we'll calculate a region of space where you're likely to find it. So again, the Heisenberg uncertainty principle is you cannot know the energy of the electron and its location with certainty. So I'm going to do a switch here. Back to here. So we're talking about the Heisenberg uncertainty principle. So a lot of people take this to mean that if you know the energy of the electron, you don't know where it is, or if you know where it is, you don't know its energy. And that's not what this says at all. This says you cannot know both with certainty. Okay, so the model focuses, and the model meaning the quantum model. I don't think that's the right spelling of focuses. Maybe it's supposed to be an S. So the models, you know what I can do here? So I can get rid of that. I don't know what to do there. So I'm going to say, so the models focus. That's my way around not knowing what to do with focuses. So the model's focus is on certainty of energy and uncertainty of location. And so that's why we have that radial distribution plot and the 3-dimensional plot. Okay, so that's psi and psi squared. Let's look at the quantum numbers. And here's what's important for the quantum numbers. a set gives the energy and location of an orbital. And what is an orbital? An orbital is a region of space where you're likely to find the electron. So when we say a set, we're talking about an N, an L, and an M sub L. That's a set. So it gives the energy and location of an orbital. Didn't realize how late it is. I'm going to go ahead and summarize this as quickly as I can. So N is called the principal quantum number. So what does Qn mean here?
What, quantum number?
Yeah, because I don't want to write that all out. Do you? L is the angular momentum. Quantum number. And M sub L is the magnetic quantum number. Now we have terms that apply to these. N is the shell. L is the subshell. And M sub L is an orbital. So the way it works is orbitals make up a subshell. Subshells make up a shell. And the difficult thing about this is that not all subshells have the same number of orbitals, and not all shells have the same number of subshells. So we're going to do this for N, L, and M sub L very quickly, and then we'll call it a day. Your homework is going to be due Thursday, or I think Wednesday. Yeah, Wednesday. And your quiz is going to be Thursday on this material. So let's look at N. N can be equal to 1, 2, 3, basically all the way up to 7. And L can be equal to 0, 1, 2, all the way up to N minus 1. So if we have, for N, L really is going to be 0, 1, 2, or 3 for all practical purposes. Now, these actually have letter designations also, SPDF. So if L is equal to 0, we call it an S subshell. Remember, this is subshell, and this is shell. So if we have a 1s, that's an S subshell in the first shell. And to give you an idea, first of all, of shells, if this is your proton, this is n equal 1, n equal 2, n equal 3, and this is the shell. And remember, this is a three-dimensional space. It's not an orbit. Tell me you're with me there. This is not an orbit. It's a three-dimensional space. Are you with me? Bohr's atom, this is an orbit. The electron orbits around the nucleus. Schrodinger's model This space is a three-dimensional space where you're likely to find the electron. So what do we notice about the different shells? They're all spheres. They're all spheres where you're likely to find the electron, okay? And the larger the n, the bigger the sphere, the more likely it is you are to find it farther from the nucleus. Okay, so that's the shell part. Now, what about the subshell part? For the subshell part, these different subshells have different orders of stability. So here, let's take a look at N and L, and we're going to look at different arrangements. So let's say we have N is equal to 1. What can L be equal to? Well, according to this, L can be equal to 0 all the way up to N minus 1. Well, N is 1. What's 1 minus 1? 0. So that means L can only be equal to 0. So you put these together, and this means that you have a 1s subshell. Now let's look at N equal to 2. What can L be equal to? It can be 0 or 1. See, all the way up to N minus 1, which is 2 minus 1. 2 minus 1 is 1, so L can be 0 or 1. This is a 2s subshell and a 2p subshell. So back to that L, I want to remind you down here that if L is 0, 1, 2, 3, we're talking about SPDF. So if L is 1, it's a P. Oh, and I'm sorry, and I forgot I want to remake this chart real quick. So N comma L, let's have N equal 1, L can equal 0. And so we've got a 1, 0, which is a 1s subshell. So this is what I've added, 1, 0, NL. If N is equal to 2, L can be 0 or L can be 1. So we can have a 2, 0, which is a 2s subshell. And we can have 2, 1, which is a 2p subshell. So let's do one more. Let's do N equal 3. What can L be equal to? It can be 0, it can be 1, or it can be 2. Because the maximum quantum number that L can be is 1 less than N. Okay, so what would we call this one? This would be a 3, 0. What kind of subshell is that? Well, if 1, 0 is a 1s and 2, 0 is a 2s, 3, 0 has to be what? A 3s. And if a 2, 1 is a 2p, then a 3, 1 has to be a 3p subshell. And here, what does a 3, 2 have to be? It's a 3d subshell. So you have to remember this order, S, P, D, and then F. And how do you remember SPDF? I remember it. Some people do fine. But you need to remember that order. So I'm going to leave this to you to figure out what are the possibilities, okay? Now, turns out that subshells are made of orbitals. And for an orbital, you need an N, an L, and an M sub L. You need 3 numbers. So here we're going to skip, well, actually we'll do the N, L, and M sub L, just like we did for the subshells. We'll do N equal 1, L equals 0. And the rule for M sub L is that M sub L can be 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. So in this case, M sub L can only equal 0. Because when we get plus or minus 0, it's still 0. So in this case, you've got 1, 0, 0. This is a 1s orbital. Now, why is it called a 1s orbital? And the answer is because it's in the first shell, it's in an s subshell, and this 0 indicates a specific type of orbital. For n equal 2, you can have L equals 0 and M sub L is equal to 0. So you'd have 2, 0, 0, and this is a 2s orbital. And then you could have n equal 2, L equal 1, and this is by far the most interesting one that we're going to run into so far. M sub L can be 0 or plus or minus 1 all the way up to plus or minus L. So here, because L is 1, M sub L could be 0, M sub L could be plus 1, and M sub L could be minus 1. So what we have here is a 2, 1, 0, a 2, 1, plus 1, and a 2, 1, minus 1. And this is a 2p orbital. How do we know it's a 2p? 2, 1. How do we know we're talking about an orbital? Because it's got this 0 here. That's a specific 2p orbital. Now here, since this number is different on the end, but these two numbers are the same as the ones above, it's still a 2p, but it's a different 2p orbital. So you can see that when we start talking about the second shell has 4 orbitals. The first shell has 1 orbital. So what I'm going to leave you with is this. Try and do this, what we've done right here, for n equal 3. Figure out the different L's, all the M sub L's, and how many orbitals you can find in each subshell. And that'll help you to kind of understand what's going on here with the rules for how we assign N, L, and M sub L. Okay? It's almost like a math riddle when you're trying to figure that stuff out. All right, I'll be posting tomorrow's lab later today. Tomorrow's lab is really going to be something that you don't need to write up in your lab notebook. It's going to be more like I don't want to call it a research paper, but you are going to do some research, but we're talking about a couple of pages at max. Shouldn't take any more than 3 hours. All right. All right. Turn on your mics and say goodbye. We'll see you Wednesday.
Bye, guys. See you on Wednesday.
See you on Wednesday.
Have a good one.
And thanks for helping me out there, Harry.